Binary and hexadecimal are two important notations in programming, but let's start first by knowing some names given to a certain bit patterns. Nibble is a group of 4 bits. A byte is a group of 8 bits. And a word is the maximum number of bits that a processor can process at one time. That is, we have 32-bit processor, which can process instruction of 32 bits, and we have most recently 64-bit processors, which processes instructions of 64 bits. So that's a word, the maximum number of bits that a processor can process at one time. This is a series of binary patterns, and this one is table with notations of binary and hexadecimal values. Hexadecimal is a numbering system of 16 with 16 possible different values for a single digit, while binary numbering system is the one that can have just two values in one single digit. We can have 0 or 1, just the two values. However, in hexadecimal system we can have 16 from 0 up to 15. However, once you've reached the value of 9, the next value that is in numbers, the value of 10, it is represented with the letter A, and so on and so forth for the next numbers from 11 to 15. We use the first letters of the alphabet. That's for the sake of representing such amounts in just a single symbol. Let's have a look at the next picture, which is an hexadecimal set of numbers. We can recognize it because we have different numbers apart from 0 and 1s. We have 6, 4, 9, and we have also the first letters of the alphabet. You can see here A, B, F, whatever. So the main advantage of this hexadecimal notation is that we use last digits. So for instance, have a look that this F value can represent 4 binary digits. That's why, because we can spend less time and effort trying to interpret these values. So we'll do a conversion of this binary number into hexadecimal. I'll tell you how we do that. First of all, we start grouping all of the bits that we have here in groups of 4 bits, and we have to start from the rightmost position, which is the lowest. It is the lowest because, just as in decimal numbering system, the lowest number is placed in the rightmost position, just like in this number 14. We know that 4 is greater than 1, but depending on the position, this one represents a greater amount than 4, because 4 is in the units digit and 1 is in the tenths digit. So the same happens in all of these numbering systems. That's why we have to do the same. So let's start by doing this. This is the lowest number. So we start grouping in groups of 4 bits. 4, 4, and 4. And we start translating these 4 groups of 4 bits to hexadecimal according to this table. So this one is 0. The next one is 1. Pretty simple. This next is the value of 10, but we are going to write A because it is hexadecimal, and this one is 9. So we translate it to a hexadecimal. You know, this is in base 16. Let's do the same with this other number. We group the entire bit patterns in groups of 4 bits, and we translate every individual group to hexadecimal, starting with the lowest, let's say. Okay, this value is 0. The next one is B. Have a look, this 1011. 1011, it is B. And the other one is A. We have already done it before. And the next one is 3. 011, 011. What do we do in these cases is that we have groups of 4, but sometimes, somehow, we may have just a few groups of bits that are left in the leftmost position. But what we do here is just start grouping from the rightmost position, and if we have numbers like these ones that do not complete 4 bits, we'll leave them this way and just translate it to the equivalent hexadecimal digit. Also, hexadecimal numbers are noted as 0x and the actual hexadecimal amount. So just ignore this 0 and the x, but just take this number, but recognize it whenever you see 0x and some expression of numbers or combination with some letters. You know, this is other notation for hexadecimal. Now let's do the same with this other hexadecimal number. We are going to do the other process. So we're going to group all again in groups of 4 bits, and we'll take all the 4 bits. I mean, this one is 2, the number 2. We have to occupy the 4 bits. So if we have just 1 and 0, we have to take all of the digits, otherwise we'll be converting this amount in the wrong way. The next one is C. So we see C equates to 1100. B equates to 1011. And this number 3, we do the same. It's wrong. The appropriate conversion should be, have a look at here, 3, 0, 0, 1, 1, 0, 0, 1, 1. So this one is wrong. So that's it. That's how you convert from binary to hex and vice versa.